Okay, so as I said, I want to start back from the last lecture that was 2 weeks ago. And the last lecture was, as you may remember, focusing on risk assessment. So I go to the lecture, risk-based adaptation design, and we got at the end of the lecture to this graph here. I get it on the web page. Okay, it's on this graph here. You may remember it. So basically, this graph visualizes, depending on the intensity of the event on the horizontal axis, which is related to the probability we said. So the higher the intensity, the lower the probability of occurrence. Displays the progress. Sorry, students, can you please avoid to speak? You can stay, but no speaking at all, okay? Because unfortunately, there is noise. Okay, thank you very much. So it displays, depending on the intensity of the event, so depending on the probability, the progress of vulnerability and exposure, because as I said, the vulnerability and exposures are dependent on the intensity of the event. So, of course, a community may be resilient against low intensity events, but can be exposed to higher intensity events. And the same for exposure. So the exposure is changing because with increasing intensity of the event, it increases the area that is subjected to damage, and therefore the exposure is increasing. So if we look this was already discussed 2 weeks ago. If you look at the red line and the blue line, clearly, you see that there is an increase. It's a non-decreasing curve for increasing intensity. And then the risk is the product of the three. So it's the product of vulnerability, exposure, and probability. Okay, so increasing intensity, again, decreasing probability. So it may happen, what you see in the figure, so it may happen that the risk reaches a top. This was the conclusion of the last lecture. And now I want to start this new lecture by discussing what is the meaning of this result. So is the meaning indicating, suggesting that we should design for an intensity of the event corresponding to the highest risk, or are there any other implications? So the meaning is the first, the main message that this graph conveys is to make us aware of the state of the system. So to make us aware that depending on the intensity of the event, there is an increase in vulnerability, an increase in exposure, and a progress of risk that may be, in a way, may evolve with different patterns. It may reach a top, it may not reach a top. So actually, this graph is not intended to give an indication of the intensity to which we should design our projects. Sorry, can you please leave the room because I can't teach if you're speaking. I'm sorry for that. I am given this room, which, yeah, no problem. Okay, I'm sorry. I mean, either you spoke just a moment ago, either you don't speak and then you can stay, or otherwise, I'm sorry. I know that this is students' room, but I am giving this room for lecturing. Okay, so as I said, the graph is not providing an indication for the intensity of the event that we should use for a design project. It's just giving an indication of the intensity of the event that corresponds to the max risk. Because actually the value of the design variable, the value of the variables that we should use for a design project is given in many applications, is given by the law, the force, is given by guidelines, technical guidelines. And therefore, I mean, once again, the meaning of this graph is not to provide an indication for design. It's just to give us an idea. So if the law suggests that I should design for an intensity of the event that is given to an assigned value, from this graph, I can understand the risk associated to that project. This is meant to be the indication. And now I want to discuss with you another question. And it is the question, the basic question of these 2 hours. So what is the other question? The other question is, what does this risk value that I have estimated with this graph mean? So what is the meaning of the estimated risk? And I said that the unit of risk is the same unit as exposure. So if exposure is given in monetary units, then risk is also given in monetary units, of course, because vulnerability and exposure and probability are dimensionless. So the unit of the risk is the same unit of exposure. So if the exposure is given in monetary units, this is typically the most frequent application, but keep in mind, not the only one. So if the exposure is given in monetary units, then the risk is given in monetary units. But what is the meaning? If I estimate a risk of 1 million euros, what is the meaning? Or if the exposure is given in terms of loss of lives, this is another situation that occurs in practical application. So exposure may be measured by the number of people who may die if the event occurs. Then the risk is number of died people. So what does it mean if I get a risk of 100 people who die? What is the meaning? This is the question I want to explore today. And I think the best way to explore this question is to focus on an application. So I want to propose to you an application, a very simple application. It's an ideal application where we can estimate the risk associated to an event. And I refer to a flood event because it's easier. It's easier, at least for me, okay? But we could also refer to an earthquake, provided we are given the probabilities of, and also vulnerability and exposure. Because if we want to apply this equation in practice, we need to be given, or we need to estimate the probability of the event. And we need to estimate the progress of vulnerability and exposure. Probability is, is a statistical exercise, as we know. Probability is related to climate change. So in the future, because I make a design project for the future, in the future I need to estimate the probability that the event occurs. And in the future means that I have also to account for climate change. But we don't discuss today how to account for climate change. In particular, we will discuss those of you who are attending the CD on climate change adaptation, we will discuss how to get probabilities under climate change in the second semester. We will give some anticipation in this course, but we will focus on it in the second semester. There is a course called Actions on Structure and Infrastructures in a Changing Climate. This is specifically focusing on estimating probabilities under probabilities and in general forces under climate change. We will give some anticipation, but what I want to emphasize now is that the probability here depends on climate change. Vulnerability and exposure generally do not depend on climate change directly. It's probability that depends on it. Vulnerability depends on the structure of the system, how much the system is protected. So it may happen that with awareness of climate change, people increase vulnerability, but it's not a direct relationship. Okay, so vulnerability is to be estimated by looking at the state of the system. So for an earthquake, for instance, are buildings earthquake proof or not? This is fundamental, a key question. And same for exposure, it has to be estimated by analyzing the system and the expected system behavior in the future, like what would be in 30 years, the value of the goods exposed to the event after evolution, after increasing, for instance, population. But it's not directly related to climate change. Of course, climate change may have an indirect relationship. because people may migrate, may leave, or may come, but it's not a direct relationship. You just have to think for estimating vulnerability and exposure, you have to think of the system and the behavior of the system, not directly to climate change. Okay, so let's try to make this experiment. The experiment, I would like to make the calculation, which is very simple, because as you will see, it's a simple experiment that we could also carry out in Excel. But I would like to make the computations into R, and I don't remember, I think we already installed RStudio, correct, in your PC. Perfect. This is very good. And it is very simple, so don't worry if our experience with R is very limited. We can learn by doing. Actually, if I go back to my web page of the course, I put here an additional link. First, note that I removed the link here, a link that we didn't discuss. It was called the climate change problem. I removed it because I added another link, and so I had to withdraw a previous one. I told you that the list of the links may evolve during the lectures. So I added a link under experiential learning, and I could have called it exercises, not just experiential learning, but I think it is nice to focus on this concept that is now becoming very popular, experiential learning. We used to call it exercises, but actually in the English language, it's I think it's more meaningful. And the learning one is this computation of risk associated to flood events. And let's just download this zip file. Let's see if I can open it without expanding it. And there is a PDF, and the exercise is computation of risk associated to a flood event. As I told you, it's very simple. And it refers to a river that may originate potential flooding. It is common practice in flood estimation, flood probability estimation. It is common practice to fit a probability distribution on the annual maxima. So we refer to data collected in the past. We pick up for each year the max river flow in that year, and then we collect a sample of annual maxima. And then we fit to it a probability distribution. Why? In flood modeling, we refer to annual maxima. First, let me say it's not the only one method that is suggested by the literature and by the technical guidelines. It's one option. It is the most classical. I don't want to say much more about flood modeling because it's not our purpose today. But I just want to mention what is the logic behind selecting, picking up one number per year. And the logic is suggested by two needs. The first need is minimize computational effort. So one thing is if you have 10 years of data to analyze 3,650 numbers. Another thing is to analyze 10 numbers. And you may say, why should we save? Why should we be computationally efficient? Because this is, as I said, a classical method. And in the old times, people were computing on paper, not on the PC. And therefore, this was a real need. Today, it's not anymore a need, but still, it is much simpler, not only in computational terms, but also in assumption that you have to make. Because, and here it comes to the second need. The theory of probability, so far, that we learned so far, models independent events. So when I toss a coin, the examples that I made, tossing a coin, rolling a dice, anytime that I roll a dice, it's completely independent. The previous result doesn't have any effect on the next one. I open and close a parenthesis. You know that people gambling, they basically try to bet over the number that has been less picked up in the recent trials. this is completely unscientific. I mean, even if you roll a dice 100 times and you never get a 6, it doesn't become more likely that the next one you get a 6. Absolutely. But in gambling, there is a long tradition on that. Like in the lottery, and in Italy, we had the extraction of the so-called lotto. It's a lottery that was extracted once a week. Probably it's still extracted, but less popular. And people were really betting on the numbers that were long not extracted. But it's absolutely so. The theory of probability, the classical theory of probability that we described so far, describes independent events. So suppose that you look at daily river flows and you get a flood like in the Romagna region in 2023 May. We got 2 floods with a distance of 1 week, or a little bit more. It was 10 days, as you may remember. Do you think these floods were independent? Absolutely not. We recognize that the second flood occurred because the soil was still wet after the first flood, and the rivers were still full of water after the first flood. So they are not independent. So if you apply the theory of probability, like the one that we discussed so far, to these 2 events, the frequency is falsely estimated, because you may say, okay, 2 events in 1 month, so these events happen in 2 events in 1 year, so these events happen on average twice in a year. This is not true, because it was only 1 event. It was only 1 meteorological event, so it should be counted once. So basically, this is why in the past they decided to pick only 1 value per year, only 1 annual maxima, because in this way they made sure the events were independent. And you can use the probability distributions that we studied so far to model them. Okay, and this is why the annual maxima is a classical. And I want to discuss this example, even if we, as I said, don't need to go into details of flood estimation now, to give you anyway an indication of how it's important when you use a model, to keep in mind that the model, first of all, the reason why you use a model is not to produce a design variable. So in engineering, several people say, what is the reason, if I ask you the question, what is the reason why you use a model? So basically, any people, including me, would say as a first reply, because I need a number to make a prediction. I need a prediction. But I mean, the first reason why you use a model is that you want to emulate a system. You want to gain a theory for a system. Because otherwise, without the theory, you can't make a prediction. So first of all, you fit a model. Okay, what is the purpose? The purpose is emulating the system, getting a theory. And then, thanks to the theory, thanks to the emulation of the system, you then apply the model. But the first thing is that the model has to represent the system. So I just want to give you some food for thought, and therefore I think this is a nice example. So probability distribution, you use that. Okay, what are the assumptions? So what is the theory behind it? For a probability distribution, an essential assumption is that the events are independent. And therefore, the annual maxima, it's an appropriate solution. No question.
Sorry, can you repeat
The first?
First need to have one.
Yeah, okay. The first need was just computational saving. Computational saving because, of course, if you have daily data, typically in river flow modeling, you have daily data. And therefore, if you need to analyze 100 years of data, because to have a meaningful representation of the past, you should have, it is unfrequent that you have so many data, but it would be nice to have 100 years of data. So if you just pick the annual maxima is 100 numbers. If you pick all the days, 36,000 and 500 numbers.
If this could be a classical method, we already take one every day, because you said for the classical method, they are in my head.
Yes. So
if we use like a computer or something else,
You can use daily data. Yes, you can, but of course you have to use a different model, not just a probability distribution like we learned so far, because you have to take into account that the events are not independent. Okay, so like it's very clear if you think about, for instance, the flow that you see today has an effect on the flow that you see tomorrow. They are not independent. So if you today you see a flood, tomorrow is still a flood day over the Porino, over a small creek. But this is to say that there are models, statistical models to describe dependent data, but we didn't discuss them so far. By the way, these are called stochastic models. It's a bad term because it looks like something very complicated. They are not complicated at all. They are very simple. And keep in mind, in statistics, everything is trivial, very simple. The theory, it becomes a bit cumbersome, but everything is very simple. Your question?
In this case, probably studies, but also as we said in the previous classes, to defend our theory from
Yes, of course. I mean, and this is the risk that if there is a misunderstanding in what you use the model for, which means a misunderstanding about the reliability of the model. So I mean, the tendency today and the trend today, because we have ready-to-use softwares, is that these models are reliable. This is the trend. We assume that if we are given a software and the software is used by many people, it's reliable. And that's not true. I mean, the software, the model needs to be tested. We have to make sure that we meet the assumptions. And therefore, this is why I introduced this discussion. So anytime you use a model, and today you have models for everything, you have softwares for everything, but anytime you use it, just keep in mind that the first thing that you have to do is to make sure that you are meeting the assumption that the model is reliable. So the first question is, what are the assumptions behind it? And in probabilities, I'm not sure I said that, but there is when you fit a probability distribution, there is an assumption behind it, which is independence of the data, independence of the experiments. And then, as I said, there is the solution if you have dependent experiments. So in this case, anyway, our exercise, let's go back to our trivial exercise, it's annual maxima. So here you see that annual maxima were observed for a even long 150 years. So we expect to get 150 numbers. And the data reported in this text file, which is in the zip, okay? So in order to use it, I suggest that, because I suggest that you follow me with the PC if you have the opportunity. So download the zip file and extract the files in the documents directory, okay, of your Windows, if you have Windows, okay. And so you get this maxam.txt in your document directory, because when you start R or RStudio, better RStudio, you get into the documents directory. Okay, so the river is protected by levees. I'm reading the text. So that vulnerability is kept to 0 up to a river flow of 12,000 cubic meters per second. Then vulnerability is increased linearly to 1 for a peak flow of 18,000. And what does this mean? It means that up to a river flow of 12,000, you have vulnerability 0. And then you have a ramp increasing, and there is the graph here, up to 1 to 18,000. And then it's again flat, because, of course, vulnerability, when it reaches 1, it's 1. It means that also for higher river flows, there is vulnerability of 1. And then there is the exposure. So the exposure is, again, varying linearly. So the exposure is null up to a river flow of 8,000. And then there is a linear increase up to a value of 12 million euros for a river flow of 16,000. Is this clear? So it's very simple. These are curves that are piecewise linear curves, okay? They are not smoothly varying like the example that I gave earlier. These are piecewise linear curves, but that's fine. I mean, it's very often when you get into practical application, it is convenient to make linear approximations. Maybe that you take a conservative approximation and then you make linear approximation. It's very useful. Okay, perfect. Now, what is the purpose of the experience? Compute and plot in a graph the risk associated to flood events for peak flow ranging from 0 to 30,000 cubic meters per second. And the purpose, the final purpose is compute the risk R by the relationship R equal to P times V times E, where P is computed with the log normal probability distribution. So it is suggested that you fit the data that are included in the file with the log normal probability distribution. And then it says, for each peak flow, use the probability of not exceedance to estimate P. And make a reasoning on the meaning of the obtained risk value. What do they mean? This is our question. And look at the suggestion. Use the probability of not exceedance to estimate P. Okay, this is something we have to think of because it was not told earlier. I said P is probability, but I didn't give any other information. I only said for increasing intensity of the event, the probability is decreasing. Remember that. This is the only thing I said, but I didn't say P is cumulative probability, is probability density. I only said this is probability and it's decreasing for increasing intensity of the event, because I said this is the probability of the event, but I didn't say anything. Here it's suggested to use the probability of not exceedance. You should already get some understanding, intuition that it's not the same thing. I'm not getting the same graph as here. Where is it? Here it is. The risk-based adaptation design, it's here. So I'm not getting the same graph as here. Okay, because the probability of not exceedance is increasing for intensity, increasing intensity of the event, if you think of it. But let's follow the suggestion of the exercise. Now, once you extracted the file, the text file, maxam, in your document directory, you can start RStudio. And let me move to another PC because something here. Okay. Okay, good. So this is RStudio. It's just open, just installed, open by brand new. Just let me view. I increase the fonts. Control. I think, let me increase it again. Okay, you may find it, you may see it a little bit different, but you recognize the structure of RStudio. There is a window which is the text file and the source code, sorry. And then there is the console here. I can just Control F, clean it. And then there are the other two windows here. Just keep in mind that you can shape the windows as you like, okay? And you can also, if you want, you can, for instance, here, if I'm not interested in the environment, I can just switch it off, okay? Or minimize it. And okay, now, what do I need? First of all, I need to upload the data, but first let me, because I need to put the data available myself. So how can I do that? Because I cannot open a software here, web page here. Just 1 second. Let me, yeah, okay, I got it. Just let me. Okay, so I can also go there. Perfect. So let me just do this. Okay, here it is. Perfect. I am done. Okay, let me see. So first of all, let's upload the file, and there is R code suggested here. Just 1 second. Is R code suggested here? And suggested R code. Let's open it. Open. And let's keep it in mind, just because it is, ideally we should avoid to use it, but just to make sure that I have something to show you. First of all, we have to upload the data. Not sure if we already discussed this. This is the function into R to upload data. It's scan, and you just have to give the file name. So if you try this instruction, and if you have the file in to the documents directory, you should succeed. So let me try it. So we can write it in the river flow. I don't remember how it was called. Okay, I prefer to call it ops data equal scan, and then I give the file name. And to see if I have it, I can use the tab. You can use the tab to complete the file name, and then you can select it and run. Okay, read character set is not UTF-8. Okay, let's try to make a plot of this. I go into the console because I got a warning that I don't understand if it is a warning that causes any problem or not. So the way to check it is plot it. Plot ops data. And let's see what happens. I think it is okay. It should be okay. These are the numbers. And let me check the length of the data. It should be 150. Yes. And let me check if everything is readable, max ops data. Because if there are numbers not readable and you make a computation, it gives an error. If it gives the max, yes, it means that everything is okay. Okay, very good. So we uploaded the data. Now let's look again at the code. We already plotted the data. Now, what we need to do is to fit the log normal distribution over the data that we just uploaded. And then we have to associate the probability to a given vector, a dummy vector of river flows, because I need to create a graph, if you remember, with the river flow or the intensity of the river flow, but let's make it in correspondence of the river flow, because it's the same thing. Intensity, I put the river flow, and the amount of the river flow is a measure of the intensity of the event. So let's create this vector of river flow to put in the horizontal axis, okay? So if I show it over the blackboard, I need to create this graph of river flow. So river flow, and here, the vertical axis, I have to put E, P, and R, okay? And therefore, first of all, I need to create a vector for the horizontal axis. And let's create a vector, the range of river flow, so range of river flow, is 0, 30,000. It's reasonable because if you remember, here there is the max of river flow is 19,000. So let's make a graph that is extended in the range 0, 30,000. And therefore, I need to create a vector. So you see the instruction here, create vector of river flow. And the instruction is, let's make a sequence of numbers from 0 to 30,000 with the step of 100. So how many numbers do we get? 301 and 1, okay. And okay, so let's make it here in our studio. Okay. So river flow. Let's put it in the I don't understand why. Okay, it was cancelled the first instruction. Let's me copy it and put it back. I don't know why it was cancelled here. Okay, and then we can write river flow equals sequence 0, 30,000, 100. Okay, good. Yeah, oops, sorry. Okay, and then we can run it. Okay, now it didn't disappear. And if we just make a check here, length of river flow, we should get, yeah, 301. Okay, good. Okay, so we got the vector. Very good, this is simple. Let's go back here and then let's see. Now we have to compute the probability of not exceedance because we were suggested to compute the probability of not exceedance for the vector of river flow. It's very simple if we assume to use the log normal distribution and we assume the data are independent. The log normal distribution is just a normal distribution estimated over the logarithm of the data. So into R, however, there is a function that allows you to apply immediately the log normal without the need of taking the logarithm. And the function is PL norm, okay? So P stands for probability, L norm stands for log normal. And of course, you have to give as argument of the function, you have to give the vector for which you want to compute the probabilities, the just created river flow, and then you have to give the mean and the standard deviation of the data. And however, the mean and standard deviation, you have to take the logarithm because they want to get mean and logarithm in terms of mean of the logarithm, not mean of the data, mean of the logarithm and standard deviation of the logarithm. So you see why there is here the computation of the logarithm of the data before taking the mean. Okay, so let's make it on the other window. And so here we are. So P river flow is equal PL norm, okay, and river flow. Now we have to compute the mean of the log, perfect, of Maxan. And then I am just going by memory. So if you say something, and then the standard deviation. So SD should be SD. Let me check.
SD log.
SD log. Okay, but yeah, SD log. Maxan. It should work. Not really sure, but it should work. Let's see. Error. Yeah, sorry. It's not Maxan, it's ops data. Ops data. Data. Okay. Now it's here, and let's try to plot it to see if it has some sense, and then I'll check if the instruction is the same as it's given in the suggested R code. So plot river flow, P river flow, and let's make it a line, type equal line. Yeah, it is reasonable, it is fine. You see the long tail, okay? And it's a typical shape of a probability distribution. Now let me compare. So it's mean log ops data. Let me check mean log. It is mean log. Mean log. Okay, that's fine. Mean. I didn't put the name of the argument here. It's not needed. Mean log maxan. Okay. S3 log. Okay, perfect. And then there is the plot here. Now, we can also plot the probability density, and it is very simple. Just if you want to plot the probability density, you take the difference of the cumulative probability of the probability of not exceedance. The difference is like a derivative. It's computed on a vector of data, so it's a discrete derivative, but let's see. And so let's go back here. I am jumping from one PC to another because I'm not allowed to open RStudio on the PC of the room. So this is why I am jumping from my PC in my office and here. Okay, so let's make it here. I want to keep a copy of the code, so let me just keep a copy here. And then here we can plot river flow, and this P river flow. No, P river flow. Okay, and then type equal line. The plot is not needed, it's just out of curiosity to see how it behaves. Sorry. Yeah, okay. P river flow, because the difference is one value less than the original vector. So here we have to put the P river flow ranging from 2 to 301. And now it should work. Let's see. Okay, this is the density, which is perfect. You see the long tail is a log normal, so we expect a long tail. It's not symmetric because it's a log normal, and it's only positive. The log normal distribution actually is widely used for modeling extremes, and along with the gamma distribution. And you may be familiar with the gamma distribution because I think that you used it last year in previous year. For instance, my colleagues at Naceola probably introduced it, and also the students of offshore engineering. The gamma distribution is frequently used to model wave data. So max, like annual maximum wave height. But the log normal is also largely used, okay? And the log normal distribution is not fat-tailed. It's long-tailed, but not fat-tailed, okay? You may remember that we talked about also fat-tailed distribution. Here the tail is long, but you see that the probability associated with the tail is low. The tail is very close to the horizontal axis, very close to zero. With the fat tail, you would give a larger probability in the tail. And but in any case, it's in theory, in the theory of statistics, there is a clear definition of what fat tail means, and the normal distribution is not fat tail. It doesn't satisfy the definition of fat tail distribution. We don't go into the details, but I just want you to make you aware of this terminology, because sometimes it is mentioned. Okay. Good. Now we have the probability, and now we have to translate into numbers the two suggested shapes for exposure and vulnerability. Good. Let's go again to our suggested code. Okay. Now you see here there is the creation of the vectors of vulnerability and exposure. They have to belong 301. So first there is the repetition of 0. There is the creation of the vectors. Remember, when you want to assign values to a variable into R, you may avoid to define it. Usually in the programming codes, keep it in mind, before using variables, it is common practice that you need to define them. Into R, this is not needed for variables. For vector, it is needed. Okay? You may wonder why we need to define variables. The explanation is very simple. The PC wants to know what is the amount of memory to be reserved. And therefore, particularly for vectors, is extremely important. This was more important in the past because we were used to have limited amounts of memory in PCs. Now, it's in a way not really a big issue. But still, I mean, the memory, the capacity of the memory of any computer is not unlimited. There is a limit. And therefore, it is reasonable, especially when you use work with big data, that you specify beforehand the variables that you mean to use in a program, because it would be very inconvenient that you start programming and after 10,000 lines of code, you realize that there is no enough memory in the PC to run your code. So this is why in any programming language, they have the brilliant idea of asking the definition of variables before using them. Into R, what they did is, okay, definition of variable is boring, so let's assume that, let's skip it, but not for vectors, because the vector may take a huge amount of memory. So vectors and matrices need to be defined also in R. The variables, they said, okay, let's forget about defining the variables because it's a complication, okay? So this is why here I am defining the vector, the two vectors. And then there is this creation of the interpolated vector of vulnerability. It is a very simple linear interpolation, but understanding it is not so easy. So let's look at this instruction that I highlighted. First of all, the vector that I created is initialized with zeros. I don't need to define the first 120 values, because up to a river flow of 12,000, the vulnerability is 0. So I can leave the vector like it is. I only need to change the vector in the ascending ramp. So let me go back here, just 1 second. This, yeah. Second. Okay. Okay. It was already here. Sorry, I got lost a little bit. And let me go back to the web page. And here. So the vector. This is, for instance, vulnerability. I'm working on it. The vector is unchanged up to 12,000, and here is unchanged after 0 up to 8,000. And then I need to make the change here, linear interpolation between 12,000, 18,000 in this case, between 8,000, 15,000 in this case. And then it's a sequence of ones. Okay, good. Let's go back to the code then. And the code is here. So vulnerability, you see that the change is starting from 121 because the first 120 values are 0. Actually, it's starting from, let me see, from, okay, let's see. It's, I don't really realize if the is 0. The first value different from 0 is 121 values or 122. Let's see. It's 0 plus 1 over 60 because from 80,000 from 8,000 to 18,000 is 60 values. Let me just think of it. Is from, yeah, it's 60 values from 12,000 to 18,000. Okay, so 0 plus 1 divided by 60, because 1 is split in 60 steps, which multiplies 121 plus I minus 121. Here you could have simply left I. Okay, I put 100 because you see the result between the result of the summation 121 plus I minus 121 is I. I just put the values for clarity. And here I think we are changing from the value number 122, which is, I mean, that's fine. I mean, a shift of 1 unit is not a problem. Probably the most correct thing would be here to put here 120. Okay, so when I apply it, we can make this minor correction. And then we have vulnerability, the vector, from the position 122 to 301 is 1. Okay, let's try to write it into R. So first, vulnerability and exposure, I have to create them. Okay, so I go here. Vulnerability is equal to repetition of 0, 301, and then I do the same for exposure, Control C, Control V, exposure, very good. Now, let's see, vulnerability. Let's see if I can do it. So let me see, and I need a 4. Thinking if probably there could be a more intelligent way of avoiding the 4, but let's make the 4 for E in 160. Okay, and then I can avoid the curly brackets because it's only one instruction. So vulnerability 120 plus I is equal to 0 plus 1 over 60 times I. I think this is, in a simplified way, we can write it in this manner. And then vulnerability 181 to 301 is equal to 1. This should be fine. Let's try. So I select these 5 lines and I run it. So no errors. Let's try to make the plot of vulnerability. Plot. I think what we can do is plot just vulnerability. Yes, it is good. You see, from 120 to 180, it is fine. Very good. Now, let's make the same for exposure, but I don't remember the limits. Let me just see. The limit is exposure 81 until 160. Okay, from 80 to 160. Okay, good. And 80 steps. Sorry, here we are. So in order to speed it up, I cut and paste here, copy. I copy and paste. So here, make a paste, and then I make the corrections. So it's exposure. Here it's exposure. Here it's 80, if I well remember. And it's from 80. And this is 80, 108. I think it is 100. And here is 160, correct. So here it's 80, not 100. 161. 301. Let's see, exposure 80 plus I. Yes. Should be okay, because and then we can run it, and then let's make a plot exposure. Yeah, should be okay. Everything is clear. You can follow me. Okay, very good. Now, what's the next step? Computation of risk. And remember that we have the open question. Okay, so let me go here. Now, we got here, plot exposure, compute risk. Okay, and here, let's compute risk first in this way. Here in the flow. So let's compute risk by multiplying the probability, which I have computed, P river flow, which is a probability of not exceedance, remember, times vulnerability times exposure. Okay, and then we make the plot. Okay, so risk is computed in this way. Let's make it here. Risk is equal to P river flow times vulnerability times exposure. Good. And then let's make a plot. River flow, risk, good, type equal line. Good. Let's see what happens. Are we ready? Run. Okay. I mean, what we get is reasonable if we think at it, because probability is reaching 1, is probability of not exceedance, is evolving from 0 to 1, and also exposure and probability, but exposure, I think I made a mistake, because exposure, I took it varying from 0 to 1. I have to correct it, because exposure is given in monetary units. It's not from 0 to 1. Why I made the mistake? Because I made a cut and paste. When I defined vulnerability, I made a cut and paste to exposure. So I have to correct it. So let me go up here. Exposure. It's not 0 plus. No, it's 0 plus, but here I need. It's not 1 over 80. It's, I think it's 12 million, if I well remember. 12, 1, 2, 3, 1, 2, 3. I think it is 12 million. And then here is 12 million. Am I correct? It was 12 million? Or... Okay, so let's repeat it. Okay. So let me repeat it. And then we can repeat also the plot. Run. Now it's perfect. It goes to 12 million. okay? And I mean, it is reasonable because the probability is going from 0 to 1, and the exposure is going from 0 to 12 million, vulnerability is going from 0 to 1. So, of course, what I expect is a curve like this. But it's not the same curve that I got here. It's not the same curve that I got here. Check. Oh, sorry. Because this curve, if you remember, had a max. So what's the problem? The problem clearly is the fact that I am using the probability, I use the probability of not exceedance. And actually, it's not decreasing for increasing intensity. Probability of not exceedance is increasing for increasing intensity. So what could be our idea? Let's try with the probability of exceedance. The probability of exceedance is 1 minus the probability of not exceedance, and it's indeed decreasing or increasing intensity. So let's use it, okay? So let me go here. It's very easy to make the change, very easy. So let me add 2 lines, okay, of computation of risk and plot. I copy these 2 lines. I go with a new line. Now it's just copied, and here I make 1 minus, very easy, 1 minus. Let me change the name, risk 1, okay? And now let's plot risk 1. And let's see what happens. Perfect. This is what I was expecting. Still, we have to reply to another question. Not another, the same question. What is the meaning of this estimated risk? So this more or less 5.5 million, sorry, 5.5 million euros. What is the meaning? Okay, this is, remember, probability of annual maximum. So what is the meaning of this 5,000? It's probability of not exceedance of annual maximum. So what is the meaning? And in order to reply to this question, and I mean, the reply to this question is very important to understand the technical value of the risk estimate, the technical meaning of the risk estimate, okay? And in order to elaborate the reasoning to reply to this question, let me try another experiment here. Let me try to use for probability, the probability density. Okay? The probability density should indeed decrease for increasing river flow, for increasing intensity of the event. So it is responding to the feature that I'm looking for, a probability that is decreasing for increasing river flow. So let me just try and remember this graph here, okay? We could also open another graphical window, but remember this, just the shape by eyes, and remember the max value. It's about, okay, 5 million is here. It's close to 6 million. It's probably 5.8, something like that. We could potentially get the max here. Let's get the max, okay? So max risk 1. It's, yeah, almost, I mean, it's, let me think. Yeah, it is, it's not 5 million indeed. I was wrong. It's like 500,000, 0.6 millions, okay? Okay, and remember, the max exposure was 12 millions, okay? And Okay, this is the max of the risk. Now, once again, let's use the probability density. Okay, in order to use it, it's very simple. Let me make another paste, risk2, and it is very simple. I just need to compute the difference of P river flow. Remember that the probability density is the derivative of the probability of not exceedance. And therefore, if I take the difference of the vector, I get it. And the only thing is that, again, the difference has a lower length of -1. So let's take the vulnerability from 2 to, let me think, 3301. Good. And exposure is 2301. Good. And now here, let's risk2. So remember the max and remember the shape, and let's try to run it. Yeah, there is a problem here. Let me see. Plot. Yeah, okay, correct. From 2 to 301. Okay, let me rerun this. Okay, same graph. Same graph. You have seen a little bit of a shift on the left because the number of values is, but the shape of the graph is the same. And let me just recall the previous one. Okay. This one. You see that the shape is precisely the same, okay? But the value 2000 against 5000. Okay, so now our original question, what is the meaning of this risk? And let me go back to the previous graph. What is the meaning of this 0.6 millions against the value of the diff? Okay, so what kind of probability did we use to compute this? We used the probability of exceedance. Of what? Of the annual river flow. So it gives the probability that in 1 year, in one given year, I get a river flow that is equivalent to the value that is assigned or higher. This means that it's a probability of getting not just a river flow of like 15,000, but 15,000 and higher. So what is the meaning then of multiplying this probability with by vulnerability and exposure? The amount of money that I get is the expected damage, the average damage that in 1 year I get from a river flow of 15,000 or higher. Okay, so this is like 0.6 millions. So it means that every year in that place, I get an expected damage of 0.6 millions of getting a river flow that is 15,000 or higher. Okay, good. Now, if I take instead the density, of course it is lower the damage because it's only the value of the expected damage for a river flow of 15,000. But in the same year, it may occur a river flow of more than 16,000. Therefore, the damage is higher. So this is the difference between the two. Okay, so when I use density, I get expected damage in 1 year of the river flow of 15,000. And then in the same year, I should add expected damage of the higher flows. So actually what I should use is, it depends on the question of course of the customer or the purpose of doing my computation, but usually we refer to, I mean, if we get protected against value in this case, because I bring vulnerability to 0 up to a value of 15,000 of river flow. What does this mean? It means that I save every year. Basically, if I want to compute the save that I get every year, I should, depends on the evolution of vulnerability after 15,000, but I should refer to the density. Okay. Let's suppose that, for instance, the vulnerability is 0 up to 15,000, and then it jumps to 1. So the modification of the graph is from the shape that I gave to a shape that is 0 up to 15,000, and then it jumps to a shape of 1. Then what I say with this climate change adaptation, okay, intervention, infrastructure, is the value that I computed with the density, because I get protected only up to that. Okay. Okay. Do you have any question related to this? I mean, it's in, yeah, please. Okay. For the design, let me try to make it in a more comprehensible manner. So, because when you make an intervention, so let me start by saying, let's not refer to the intervention. Let's refer to the situation that I get from this graph. This graph refers to the probability of exceedance. This means that every year for a river flow of, let me just see the max, 15,000. So let me just write V line, or I don't remember if it is vertical line. No, it's a B line, maybe. Yeah, B line. Okay. And let's see, it's 15,000. Let me see if I can draw now. Okay, now I should leave it. A line V equal 15,000. So what does this mean? This curve that I got here, it means that for a river flow of 15,000, I may expect a damage of about 4.58 millions every year, given by a river flow of 15,000 or higher. Okay. If I use only the density, is giving to me only the value that I save every year for a river flow of 15,000, but I may get a higher one. And then I think this is the concept that you should get. And then if you make an intervention, then it depends on how you change the vulnerability curve or the exposure curve. And then you compare what you say for a given river flow or for a given river flow or higher every year. So when you make a cost-benefit analysis, let's suppose that then, let's refer to this graph, and you bring the cost down to 0.4, it means that you save every year about 180,000 euros by river flow of 15,000 or higher. And usually this is what you are interested in, because we are not interested in a very specific value of river flow, okay? And you are interested in saying, okay, I want to get protected up to a value of 15,000, and then the other flows that are superior, they basically make you vulnerable. All of them, not only one. Okay, so usually what we use is indeed the probability of exceedance. And if you use the probability of exceedance, you, for instance, let's suppose that you decide to build an infrastructure like a retention basin for floods or a dam for floods, that after the a river flow of 15,000, this infrastructure becomes ineffective. So is ineffective for all the higher flows, and therefore you are interested in the probability of exceedance of any higher flow. And then you refer to this graph. This is typically what we use. Okay.
So data is related to the river base.
You want to see the river flow data set?
No, I understand this range is related to a rate, to a speed, or to the number of years.
Okay, so this saving that I am computing here is related to a given intensity of the event. So to go back to our theory, and the intensity of a flood is measured through the river flow, typically. So if it was an earthquake, I should have depicted along the horizontal axis the Richter scale, for instance. And so in flood modeling and in flood mitigation, we use as a measure of the intensity the river flow. This means that to any river flow, we associate a probability, in this case, of exceedance. And therefore, with this probability of exceedance, you estimate the risk. And the risk is a damage. The risk is a damage. But remember that when we use probability of exceedance instead of probability of not exceedance, the concept is the same. What is different is the meaning of the result. But the concept is the same, because you can pass from one to another, and you can also pass to the density, as you have seen, with a very simple computation, because exceedance and not exceedance are complementary to one, and density is just the difference of derivative of the probability of not exceedance. So, I mean, what is important is to understand that the concept, there is no conceptual difference in using one probability or another probability. It's the same concept, it's a probability, but of course, the value, the technical value, the meaning of it is a bit different, and you have to understand this difference. And I think this experiment is interesting because it helps you to understand that probability is a very simple thing, basically, because you see how it's easy, it's based on the frequency of the data, how it's easy to estimate probability of not exceedance, probability of exceedance, and probability density. So probability is very simple, and you can understand really the difference between using one expression of probability or the other one. The difference is just a technical difference. It's not a conceptual difference. Yeah, correct. Yes, the river flow is defined as the volume of water that passes along the river in a unit time. So typically is measured in cubic meters per second. Okay, and of course I said the river flow passing along the river. It's not a correct definition. I made it simpler to understand. But first you should define. So let's suppose that you have a river. I think it's an interesting story, so I tell you. Let's suppose that you have a river. And then within the river, we make an assumption, usually in technical computation. You can remove it, but usually we make this assumption. We make the assumption that in any point of the river flow has a unique velocity vector. So here, I suppose that the velocity vector is this one. What does this mean? It means that if I take a perpendicular plane to this velocity vector, all the particles of fluid, microscopic fluid particles that are passing through here at the same velocity vector. Okay? Same direction, same volume. Which is not true, of course, because in a river section in general, like here, you have a curve, Okay, so you have a velocity vector here, and here you have a velocity vector that is like this. Why? Because the velocity vector is always, if these are the river banks, it's always parallel to the direction of the river bank in that point. So basically, it's not true, but we make this assumption to simplify it. So you say, okay, so let's suppose that here, instead of two velocity vectors, I have only one. This one.
With the starting one.
Sorry?
With the starting one.
Yeah, it's an average. Okay? It's an average, but actually we assume that it's the same. So basically, this means that for any river point, you can, so I take a point here, I can estimate the velocity vector, okay? And if I take a perpendicular plane to this velocity vector, like cutting the river, then along this plane, all the fluid particles have the same velocity vector. So what I obtain from cutting the river is a figure like this. It's a cross section. Okay, this is the river level, and now I am looking at this in this direction. I'm looking at this cutting the river from downstream to upstream. So I go downstream. I look at it, and what I see is this one. This is called river cross section. It's defined river cross section. And then, in one circle, you can measure the volume of water that passes through this river cross section. And this is very good. Okay? It's just called entire portata fluviale. And it's called in English also river discharge and or water flow, but usually in the technical literature you find river flow or river discharge, the same. So for instance, in the graphs you may see pour river flow, pour river discharge, it's the same, or discharge, I don't know. All the pronunciation also depends on American and English. And also the use of river flow instead of river discharge may vary in the United States or the UK, but everybody understands. If you say river discharge or river flow, it's they are treated as synonyms. Okay, but in any case, this analysis refers to any possible event, and so I mean this risk that you estimated in a way. It is to be used in cost-benefit analysis. And therefore, you compare the cost of the intervention with the damage that you save every year. And then you say, okay, I make a dam, and the dam is expected to last for 50 years. And the dam costs like 500 billions of euros. And then 500 billions is too much. Let's say a dam may cost 5 billions. Okay, so depends on the size of the dam, of course, many things, but the order of magnitude is like 5 billions, and then or could be even less. But anyway, and then let's compute the estimated saving. And then, of course, you have also to add to the construction cost, the management cost, and the maintenance cost, and you make your cost-benefit analysis. So the purpose of risk estimation is precisely to make a cost-benefit analysis, which is often done in climate change adaptation, because unfortunately, very often the costs of intervention are huge, and therefore you have to evaluate whether the intervention is doable. And typically what happens in climate change adaptation is that if you use the more pessimistic predictions by climate models, you obtain interventions in order to adapt that are very costly, and that there are no resources to make them. And then the conclusion is that administrations very often do nothing. And you understand that what is the problem? The problem also of uncertainty of climate predictions, because with a more reasonable climate prediction, you obtain a cost that is lower, and you may obtain room for action. So this is what we engineers always say. Look, uncertainty of climate models is extremely important because it's one of the reasons why we don't do anything. And so what is the solution then? We will discuss it, okay? Because of course there are several different possible solutions, but one very trivial solution is, let's try to make the system resilient first against the current climate. So let's estimate the risk in the current situation. What is the cost? Is this a cost that is affordable? No. Okay. So let's forget it. No need to make a climate prediction. It's not affordable, even in the present climate. Let's forget it. Is it affordable? Yes. Okay, perfect. Now, let's see what is the cost, and then let's see if everything is clear, and then let's verify it to the future climate. It doesn't work. Okay, so next question. Is it possible to adapt the intervention? So I make the intervention now. Now it's working. When it becomes not working, can I adapt it? Okay, yes, you can adapt it. Perfect, that's fine, let's make it. No, you can't adapt it. Okay, is there a solution that can be adapted? Or another question, okay, I can't adapt it, fine. Is the solution a possible regret in the future, or it's a no-regret solution? No-regret means that, okay, until it works, that's fine. When it doesn't work, no problem. I don't get any damage. So in any case, I get some benefit, because up to for 10 years, it's working. So let's make it, because if I get a benefit, because even if it works only for 10 years, let's make it. And then in 10 years from now, maybe we have climate models that are more effective, are more reliable, less uncertain. In any case, I have no regret. Yeah, of course. Yes, because this gives to you the expected saving for 1 year. And then if it works for 10 years, you can estimate the expected savings. Or maybe that in 10 years, the benefit decreases because it becomes, the climate, it changes the probability, and then you have to update the probabilities, but you can make the computation. And if the solution is no regret, okay, yes. So the keywords are adaptation, no regret, and adaptation of the intervention, I mean, and no regret, for instance. But we will discuss this in detail. And this is part of an interesting discipline called decision theory. And we will dedicate some room to decision theory, not in the afternoon. In the afternoon, what I plan is to make a discussion that is less quantitative on the climate system, because we also need to understand how the climate system works, how the models work. Because again, when we use future predictions, we use data, we use the results from models, we need to understand how they work, because we have to grasp the theory behind it. Okay, any question also from the connected students? So let me just see. Okay. See you then at 2 p.m. sharp. Thank you very much.